Hello everyone, my name is Ivory and then I'm a software developer in the Hand Lab at UBC. In this video, I will introduce you the Ivory OS, which is an interoperable software that can help design and control robotic workflows over self-driving labs. So I will briefly explain how we achieve this plug-and-play web UI design, and then I will give a quick demonstration of how to use some key features of Ivory OS using an abstract SDL Python script. And at the end, I will also demo some real robotic workflows using our self-driving solubility platform. So, in general, developing interoperable software for self-driving labs is very challenging because, as you can see, every SDL is different. For example, here we have a full chemistry system, we have two robotic arm central platforms. So, the top one is designed for kinetic studies, and the bottom one is for studying crystallization solubilities. And for those systems, they all have very different layout and functionalities because, again, they are designed for different research objectives. So if we wanted to interact with such robotic system and maybe design a workflow on this SDL, then we have to quickly understand the capability of such SDL. To achieve this, we use the Python built-in inspect feature and we look into the current SDL Python script. So we're gonna find all the instances that are related to hardware control. For example, on the current platform, it could be the automated balance, a local handler. This also could be the high-level user functions involving multiple devices in the robotic arms. So for each hardware control instance, we're going to further look into their class and find the available functions of this hardware. And for each function, we're going to look into their parameters to see what kind of parameter type or default value for calling these functions. So in the end, we will have the platform snapshot, which is capture the current state of the SDL system. And then we use this information to generate an interactive platform for each function. And over the control interface, we display all the functions for each instance as cards, and users can just fill in the parameters and call those functions to interact with your robot. And alternatively, instead of calling these functions right away, we could also add the function into a workflow design. By stacking multiple actions, we could have our own experimental workflow. And in the execution interface, we will have multiple options. For example, simply repeating the workflow for how many times, or have more advanced adaptive experimentation if we have the output to optimize. And on top of this, we also have a database interface where you can save and manage your workflow. It's probably from different platforms or from different authors. So again, we achieve this interoperability by dynamically inspecting the current SDL Python script before launching the web app. So the web interface will capture the current state of your robotic control script and make it adaptable to any other platforms. In this part, I will show you how to install and use some key features of Ivory OS. So let's start with installation. So over the terminal or command line, you can type pip install Ivory OS, and this will take a while to install all the packages. I already had this installed, so let's move into the Python scripts. In this one, I've imported two classes, which are the abstract pump and balance, pretending this to be the high-level SDL functions that have five user functions and then one private function starting with underscore. So the private function is now going to be extracted to the web UI, which is like by default not available to the user. And below that, there are some constant values. And now here we have the instance of your hardware module, the pump balance and the high-level SDL functions. In the same script, I import ivoryOS and then start running the UI using the current script. So by running the script, it will give me two addresses. The first one is the local host, and you can only access this through your local computer. But the second one, it will be available on your network, means any computer that's connected to your current network would have the access to this address, and then should be able to control your current robotic platform. So I'll simply use the localhost link. It will show you the login page, but if this is the first time you're using this app, then you can create a new account. This will be an account created in the local database. I already have my account created as admin, so I'll just log in to my account. So once you log in, you will see the welcome page. There are a couple of options, and those options will be also displayed in the top navigation bar. I will start with the device control interface. So in this page, you can see the instances that we have initialized in the Python scripts, balance pump and the SDL. I will use the SDL as an example. So as you can see, it's a step-by-step comparison to the Python scripts. All of the functions are extracted with the parameter input as a input box. I will simply click the dose solid function, and as you can see, it's pretending it's dosing solid, and it will return the output value over the top message panel. So this one is an oversimplified script with only 5 functions, but in real world, there definitely could be more than 5 functions in one Python class. So if some of the function is not very frequently used, then you could have the option to hide this function for now from this user interface. Um, in the same time, you can also toggle the card sequence, and uh, in this way, you can customize this interface depending on how frequent you want to call those functions, so it's more effective and user friendly. So now let's get into the workflow design interface. So in this page, on the left-hand side panel, you will see the built-in Python operations like the logic function, or you can set your own variables, or in this wait function, you can set a period of waiting time. So for example, I would just let it wait 1 second and add this to my workflow design. Over the design canvas, you can see 3 options in the top navigation bar: the prep, experiment, and cleanup. So these are the 3 phases of one experimental design. So in prep and cleanup, there will be only executed one time before and after the main experiment. So now to complete this design, I will pretend I'm going to dose some solid, and then dose methanol as my solvent. Once I have those actions in my canvas, I can also drag and drop to toggle the action order. And once I'm ready, I can click to compile the script and run. So because in this script, all of my parameters are a fixed value, so the only option I can iterate is by repeating in defined times. So in this case, I will just run this for 3 times. So you can see a process bar showing the current progress and log panel showing the current iteration steps. And once it's done, it will proceed to the cleanup execution. So in my last design, I only have fixed parameters, means I can only repeat the same workflow over and over again. But for more flexible iterations, I would have to define which parameter that I wanted to configure in the later iteration steps. So for example, in dose solid step, I would, instead of dosing 5 all the time, I would just use the pound notation and to name this variable as amount. And I will save the change to the workflow and compile it. there are 5 entries where you can input different parameters for different iterations. So now I will just input some random numbers, and you can also add more entries if you need more iterations. So now I will run this 6 experiments. So while it's running, you probably noticed there is a abort action button. So if you find that the rest of the iteration is not necessary, you can click here. It will try to finish up the current iteration, but abandon the rest of the iterations that is waiting to be executed, and it will go. It will proceed to the cleanup steps. In the control panel, we have very limited space to input parameters. So in case you have more than 5 parameters to input, you can also choose to use the Excel configuration, where here you can download an empty configuration file and then open that in the Excel. The first row is showing all the parameter names, and then the second row is showing what is the expected input type. Using the column A, you can input as many as entries and then upload this Excel file back to the system to iterate the current design. So now back to the design, and if I would love to configure a output value, for example, how much amount I dosed using the automated balance, for example, I want to save this as mass for my output. So now I save this back to the workflow and I compile it. So now you will see the Bayesian optimization option is available. In this control panel, it will generate all the inputs for all parameters and objectives. So now we can just input the range in for objective. It has to be numerical, so we'll just choose to maximize. But for any non-numerical value, you can choose to none for not optimizing this output. Now I will just simply run this 15 times to demonstrate how this works. In this last example, I will demonstrate how we can capture all the changes that's happening in the Python script. So back to the design page, we can see the analyze function. It doesn't take any parameters. And if we want to change this function by adding one parameter, for example, we can add sample name, and this is a string value, means it's just text value. And we also going to set a default value saying this is test. And we're going to rerun this web app. So now, as you can see, when I click the analyze function, there is one parameter being added to the web form, which is the sample name with the default value being test. In this section, I will use the actual robotic platform to demonstrate how we can use Ivory OS to design and control the external workflow. So in this current Python script, I have a couple of instances imported from the main workflow, including the first high-level experimental ready-to-run module and a couple of hardware handling. And in the same script, I import ivoryOS and start building the web UI on this current Python script. I will skip the login part and go straight to the workflow editor. So here I will start with transferring the vial from the vial tray and then move it to the same location at the simmer shaker. Then I will set the arm back to its home position. And now I have my workflow. I'm going to compile it. Since I can only repeat this workflow, so I'll just run this one time. Now the robotic arm can slowly approaching to the file and then take it to the thermal shaker. So once it's done, it will go back to the home location where it gets started. So now we have the file on the thermal shaker. I'm going to use the high level function. Here is the wait while, and I'm going to grab the file from location A1 in this case to the balance and then wait out the current file. I'm going to compile this and also run this one time. So now you will see the robotic arm is trying to pick up the file from the servo shaker, and it will try to rotate 180 degrees all the way to the left hand side of the deck and slowly put it onto a file holder. So this holder is specially designed to securely transfer the file onto the balance. So now the arm is waiting for the quantos to tear, and once it's done, it will rotate its forearm and to its horizontal layout, so it will be able to transfer the file holder into the balance. So after placing the file holder onto the balance, the arm gonna back out, and the Quanos will close this door and take up the weight rating of the current object. So once this process is done, the arm gonna pick up the file, twist it back, and transfer it back to the thermal shaker. So hope this video can help, and enjoy the rest of the robotic workflow.